Gibbs free energy for any equilibrium reaction is related to the reaction quotient by this formula right here, where delta G of the reaction will equal delta G node plus RT times natural log of the reaction quotient. So at equilibrium, delta G equals 0, and the reaction quotient will equal the equilibrium constant. So if you substitute for these values in the expression up here, that is going to give you 0 equals delta G node plus RT natural log of K, or delta G node equals negative RT ln K. When you have an equilibrium constant significantly larger than 1, this is going to make the natural log a positive number, which will make the whole term here a negative number, or make delta G a negative number, which will make the reaction spontaneous in the forward direction, or favor forming the products at equilibrium. If the equilibrium constant equals 1, that will make the natural log equal 0, and that is going to make delta G node equal 0, which will mean that both reactants and products have the same favorability at equilibrium, or the same amount or the same concentration at equilibrium. If you have an equilibrium constant smaller than 1, that is going to make the natural log a negative number, which will make delta G node a positive number, or mean that the reaction is actually spontaneous in the backward direction, or it favors the reactants more than the products. If you want to calculate the equilibrium constant for this reaction, if you know that delta G of formation of water equals this value right here, you can go back to chapter 10 to find delta G of the whole reaction using the products minus reactants math. You will calculate delta G for the reaction, and it's going to be a positive 474.4 kilojoules per mole. And according to the formula right here, if you have a large positive delta G for the reaction, that is going to be automatically telling you that you have a significantly small equilibrium constant that is significantly smaller than 1, which means you should expect your reaction to favor the reactants, not the products. For this reaction right here, if you know the equilibrium constant for the reaction, or the solubility product of the salt, you can actually calculate delta G for the process of dissolution of this salt in water. So you'll use the same equation, delta G equals negative RT ln K, and you substitute for the numbers. That's the value for the gas constant, that's the temperature in Kelvin, and that is the solubility product constant for the salt. And you solve for this, you get a positive 56 kilojoules per mole, which again indicate that this is a reactant favored equilibrium. It is actually, and it favors precipitating the salt, not dissolving it. The large positive delta G indicates that silver chloride is very slightly soluble. The equilibrium is mostly shifted to the left, to the solid form of the salt, not the soluble form of the salt. As we know, the equilibrium constant equals the exponential of negative delta G divided by RT. So if you take the natural log of the equation, the natural log of the equilibrium constant is going to equal negative delta G divided by RT. But we know that delta G equals delta H minus T delta S. So if you substitute from here to the equation here, the natural log of the equilibrium constant is going to equal minus delta H divided by RT plus delta S divided by R. So if you plot natural log of equilibrium constant versus 1 over temperature, the slope is going to be negative delta H divided by R, and the intercept is going to be delta S divided by R. So from the temperature dependence of the equilibrium constant, you can actually know very important information about the enthalpy of the reaction and the entropy of the reaction.